welcome Dr. Soumya Sridhar, madam, postdoctoral scholar from Pittsburgh University. She will be focusing on challenges in processing of additive manufacturing parts, steel parts. I want Srividya to introduce her. Srividya.
Good morning, one and all. So before starting the session, let's have a brief intro of our today's speaker, Dr. Soumya Sridhar. Ma'am has pursued her dual degree, MTech plus PhD in Metallurgical and Materials Engineering from Indian Institute of Technology, Madras in 2018. She served as Senior Project Officer in IIT Madras during 2018 and 19. Currently working as postdoctoral associate in University of Pittsburgh since 2019. Her research interests include integrated computational materials engineering design for functionally graded materials processed by additive manufacturing, development of thermodynamics databases using calculation of phase diagram methods. She has many publications in very reputed national and international journals. She was also honored by many awards such as Editor's Choice Article 2020, Research Award 2017 in recognition of quality and quantity of research work done during her PhD. Larry Kaufman Scholarship in 2016, Institute Merit Prize 2014 for our best academic record in MTech. We are glad to invite you, ma'am. Ma'am?
Yeah, thank you so much for the introduction, Srividya. Thank you so much. So can I share my screen now?
Yes, ma'am.
Yes, madam.
Oh, yeah, okay. Thank you. Yeah, and here we go. Yeah. So good. Okay, good morning, everybody. It's morning in India, but it's midnight in the USA right now. So I'm Soumya Sridhar, and Srividya has already given me a fair amount of a good introduction about me. So let me go directly into the talk. So I'll be talking today mostly about, just a minute. Okay. So about the ill effects of porosity on mainly the mechanical properties of additively manufactured steel parts. I do know that these sessions are mostly related with novel materials, but today what I want to show is how additive manufacturing can be applied to an age-old material. An age-old material which has been studied for the last 70 to 80 years, but mainly a weldable material, a material that is used for welding. Now, how to apply additive manufacturing, and one more, and some research lessons out of it, I would say. Sorry. Yeah. So first, the material what I'm going to talk about is copper bearing high strength low alloy steels. So as the name says, yes, it's a high strength, low alloying content, but has copper. And these are mainly developed for naval applications. And the three main key features, the three key features for the steel are: one is their high strength, as the name says, excellent low temperature toughness. So as I mentioned that it is for naval application, so it has to stand in the sea, and it has to be the sea temperature, like ocean or something, it will be like pretty low, like -20, -40 degrees C. And yeah, the ductile to brittle transition has to be pretty much lower temperature. Otherwise, best example is a Titanic ship. Titanic went and hit and broke because it reached the ductile to brittle transition. So it should have excellent low temperature toughness. And third one is good weldability, because these are so we all know that while building a ship hull, the plates are welded together. So good weldability. So there are different grades of HSLA steels available. And if you see, generally their names will be called like HSLA 80, 100, 115, as I have shown here. I mentioned here. These 80, 100, and 115, actually these numbers denote the minimum yield strength in KSI. Since it was developed in the US, they simply put the imperial units, but yeah, it's in KSI. So 100 KSA roughly comes to around 700 megapascal, basically. So the minimum tensile yield strength should be 100 KSI, let's say it's HSLA 100, should be 100 KSI or somewhere close to 700 megapascal. Now, why these were developed? Like, mainly because we know that high carbon content is going to have difficulties in welding, and for naval applications we need weldable steels. So copper bearing high strength low alloy steels with low carbon content were developed mainly for the purpose of improving the weldability. Next, why copper bearing HSLA for naval application? Why? So if we see the reason why this has been chosen is mainly because first let's see what are all the applications. First, it's going to be used in submarines, offshore structures, line pipes, and ship hulls. So the main application is ship hulls, so which is going to be directly in contact with the seawater. Now, the main point is that here, like when the yield strength is good, so please forgive me that I added mostly in KSI, but I've also given the corresponding values in megapascal for you to have a strength, to have a sense of what is the strength value should be. So some 55 KSI to 80 KSI increase in yield strength, the weight reduction is nearly 800 tons. It's a huge number. And so it's a weight effective way of dealing with the material. And second thing is, again, we are going to have very good weldable steels. Steels with very good weldability means we are reducing the fabrication cost. And how the weldability has been improved, like having lesser constraint on the welding parameters, and most importantly, no preheating. No pre in high carbon steels. The problem is you need to have preheating to increase to reduce the cracking in the heat affected zone. Now that is what we are trying to avoid here. No preheating and lesser constraint on welding parameters. And among the steels which I mentioned, HSLA 80, 100, 115, and so on, HSLA 100 is more or less very popular. HSLA 100 and 115 are like very close in composition and strength, like they are like very close. So HSLA 100 is the mostly sought after steel. And why? So let me go one by one what's going on. So the carbon, I'm talking about low carbon steel. So what is the carbon content? It is less than 0.06 weight percentage. Now, why this carbon is, this amount of carbon is chosen? So this is, let me switch on the laser pointer. Yeah. So that is because of this Gravel weldability diagram. And you see here, it's a plot between the carbon content and the carbon equivalent, which is calculated using this formula. It's completely empirical. If you see here, there are three zones. Zone 1 is going to be, if your composition is in zone 1, then it is going to be safe under all conditions. Zone 2, it may fail or may not fail. Zone 3 is going to fail without any doubt. So we have to choose a carbon composition and a carbon equivalent such that the weldability is always going to be restricted in the zone 1. So that is the reason why this carbon content has been chosen. And secondly, this main problem of hydrogen induced cracking. This hydrogen induced cracking is actually a delayed fracture. It can is happening because of hydrogen. Of course, it is standing in water for a long time. So there is always a possibility for hydrogen to enter or something like that. And the problem with hydrogen induced cracking is that there is no guarantee that it will fail immediately. After the hydrogen enters and creates the embrittlement, it can either break today or break even after 2 months. So that is the problem with hydrogen induced cracking. Now, we all know that the weldability is mainly evaluated based on how strong your heat affected zone is, because the heat affected zone is the first one which is going to fail in a weldment. So the point here is this: we are improving the weldability by improving the strength and toughness of the heat affected zone. Okay. Now, one problem solved. We have reduced the carbon content, but we all know that carbon is the main strengthening element in steels, and we are going to reduce it. And how are we going to compensate for that? And for that, the main addition is copper first. So copper is being added. That's why it's a copper bearing high strength low alloy steels. Copper is going to induce a precipitation hardening by forming pure copper precipitates, or sometimes even called as clusters. So this is going to balance the loss of strength due to the lowering of the carbon concentration. Now, so it's like a nested problem. If you reduce the carbon, the strength is gone. Now you're adding copper to improve strength, but copper is an element that segregates in the grain boundaries and causing hot cracking. And to compensate that, you add nickel. And finally, we also add molybdenum for precipitating another type of precipitates, which are called the M2C, where M corresponds to molybdenum. So this is another type of carbide, one type of carbide. And in order to precipitate another type of carbide, which is commonly found in the steels, we add the niobium, which is going to precipitate the niobium carbides. And these are called the pinning particles. That is, they're going to sit in the grain boundaries during the austenitization process, and they're going to inhibit, that is typically stop the grain growth. So that's why niobium is added. So these are all the major alloying elements in HSLA steels. And if you typically see their contents, moly and niobium is going to be like less than 1%. Copper will be between 1.5 or so, between 1.5 and 2, and nickel will be around 3%. So if you see in literature, there are several HSLA steels with several ranges of composition of different elements. But what I'm going to deal with in this talk today is a low carbon steel with carbon content around 0.06, less than 0.06, with close to 3% of nickel, 3% nickel concentration, and close to 1.4 or 1.5% of copper. Now, another important, interesting thing which I would like to introduce here is the systems design chart for material evaluation. How are we going to evaluate whether a material is going to be suitable or not? It's not like always we can bring a new material from the universe and do additive manufacturing. Sometimes we have to just take an old material and evaluate whether it is going to work for us or not. And for that, we will be using the systems design chart. Basically, if you see, there are 3 blocks in this system design chart, one corresponding to the processing, one corresponding to the structure, one corresponding to the properties. And all this put together is going to give us the performance. So in a systems design chart, you will see how the structural features are linked with the processing, or linked to the properties, and also how the structure is linked with the processing. Now let's take and these connections between them indicates what is the relation. So let's take the simple case of this strengthening precipitates here in the structure. The strengthening precipitates is responsible for mainly 2 things, mainly 2 properties. One is the yield strength, another one is the elongation. Okay. Similarly, if you see the matrix, which is, so this is the systems design chart for HSLA 100 steel. So if you consider the matrix, which is has martensite, bainite, and amialins. For those who are not familiar much with the phases present, martensite is a hard phase, bainite is a soft phase. That will be easy to understand. So the matrix structure is going to influence the yield strength, the elongation, and the printability. Printability here corresponds to like whether there is cracking or porosity or not. So again, the defects is going to affect the stress corrosion cracking resistance and the yield strength. Okay, so it's like this, we create this structure property linkages and processing structure linkages. For example, tempering is going to, the tempering process is going to affect the strengthening precipitates, because this is the stage where the strengthening precipitates form in the material, and another one is it is going to affect the matrix. So this is how, if we have a thorough idea, then a material can be evaluated to figure out whether additive manufacturing can be applied or not for a particular material. And what are these numbers which I have added here? So these are all called the design targets. So we are working for like, this is a project from the US Office of Naval Research, and they have design targets already laid out for different steels. So HSLA 100, as I mentioned, yield strength has to be 100 KSI. Apart from that, they want an elongation greater than 16%. So if we are designing a process, a particular processing technique for a commercial material which is already in use using the traditional manufacturing techniques, we need to make sure that all these design targets are achieved. So in that way, that material will pass through for further use for to be applicable in a particular application. In this case, the naval application. So additive manufacturing. So this is just a primer. I think many would have spoken a lot about additive manufacturing. For the sake of a continuity, I am just giving a few points about it. Additive manufacturing is a process for fabricating, yes, layer by layer fabrication using 3D numerical models, which is completely different from the traditional subtractive manufacturing technologies. Like you don't take a big billet and then machine it or something to get the process. Rather, it's like you're adding layer by layer to get the required part what you want. And one more important thing we need to keep in mind is a near net shape forming process. And how do we classify it? So there are loads of parameters based on which it can be classified. But mainly, if we have to see, it is based on material. I think I'm a material science person. So from material science point of view, I find these two to be the most important classifications. One is based on material feedstock. That is, you have a powder bed process, powder feed process. That powder bed is nothing but the LPBF, that is the laser powder bed fusion, or they also call it SLM, selective laser melting. Powder feed, that is the directed energy deposition, DED. This is powder feed. Another one is wire feed. So instead of the powder, you replace the powder with wire, because there are a lot of weldable materials available today, which can be where welding wires can be used for additive manufacturing. That is the layer by layer deposition instead of powder. So this is the wire feed, and it's a more cost-effective process. And this is the wire feed process is one of the processes where we can think of building larger parts. Like if I also work on wire feed additive manufacturing, we have built a tube which is almost, I would say, like 150 to 200 centimeter long, which is not possible using a powder bed process. And secondly, the energy source. So mostly the most common is laser beam. Typically, most of the materials can be processed using laser beam, and some of the materials using electron beam. But the problem with electron beam is that your bed temperature is pretty high, the powder bed temperature, due to which certain materials will have difficulties. But since it is kind of a preheating, the cracking is typically low in electron beam. And third one is the electric or plasma arc. So typically this electric or plasma arc is used for wire feeding. So this electric or plasma arc actually means like all the old welding machines are being converted to new additive manufacturing machines, as simple as that. Now, due to the outstanding mechanical properties and this, so in a nutshell, if you want to say, all weldable alloys can be applied for additive manufacturing. No doubt about it. But are we going to get a good build or not? That is what we have to figure out. And so the outstanding mechanical properties and weldability of the steels is going to make them a potential candidate to apply additive manufacturing. So what we have done is we use the laser powder bed fusion technique for fabricating HSLA 100 steels for the first time. So this is a new material, not a new material, but a new material for which additive manufacturing is being applied. And we are doing it using LPBF, which no one has done for this material. So we really don't know what parameters to use. So generally the machines come with factory default parameters for several materials, like a stainless steel 316L or Inconel 718 or titanium 6 aluminum 4V and so on. So since we are dealing with a steel, we first started with a stainless steel 316L steel to get the build and see whether it is successful or not. So instead of me showing some schematics, I thought I can just try to play some, sorry, okay, try to play a video here which was shot during our printing of the HSLS steel powder. Now you see that the recoater is going to spread a uniform layer of the powder, and the laser is gonna hit. And we are trying to build tensile bars over here. It's like it's our build plate dimension is 250 mm cross 250 mm. And if you notice carefully towards the end, there is something that is going to go around along the periphery. Yeah, so that fast thing that is going on, that is basically done to create a better surface finish, which is called a contour, a contour print actually. So you see here now it is more or less the laser scanning is going more or less parallel to each other. Yeah, so I think it won't run long, probably. Yeah, so this is the layer 1. So let me go to the next layer 2, how it is being built. So that layer 1 has been built now. Now the recoater is going to spread the next layer of the powder. And here we go. Please see the orientation of the laser. We are rotating it, right? So initially the first layer was completely horizontal, and now it is like it's slanting at an angle. I think typically we use an angle of 66 degrees. Close up view. Yeah. So that this is done mainly to avoid residual stresses. So layer 1, if the scan is like happening, the rastering is happening parallel to each other, means here in layer 2 we are rotating it by 66 degrees. Again layer 3 horizontal, layer 4 66 degrees. So we do this complete change so that to this rotation, scanning rotation for every layer to avoid the buildup of residual stresses. So yeah. Okay, now, sorry, give me a minute. Yeah, so here I'm showing a build plate. Let me switch on the, yeah. So this is the build plate. This is a 250 mm cross 250 mm build plate. And this we have built certain, these are basically fatigue bars which we built recently. And you see that we don't keep the we don't give the samples parallel to each other. We slightly slant it a bit by 5 degree, which has a particular reason. But yeah, so these are all the horizontal prints, and this is a vertical print. So this is a vertical tensile bar. I hope it is visible as a tensile bar in certain direction, but yeah. So these are all vertical prints. So typically when we do prints, in order to study the effect of orientation, we build horizontal bars like this, vertical bars like this, and also bars that are slanted at 45 degree to the build direction, to the perpendicular direction. So in order to study the effect of anisotropy on the mechanical properties, we generally do, but mostly horizontal and vertical should suffice in most of the cases. So just wanted you to show the, what to say, just wanted you all to see how the build plate looks and so on. So coming to the important thing, the role of porosity. So always porosity is a problem in most of the cases, but here in the case of AM parts, mainly two types of properties are going to be affected. First one is the mechanical properties, where it is going to affect the tensile strength and the elongation by acting as local local stress raisers. However, the pores will also affect the corrosion resistance, because again, pores are nothing but pits, and which can be viewed as a primer for pitting corrosion. So the corrosion rate within the pits will build up because of severe electrolytic conditions, leading to a stable pit growth. And a small pit which goes throughout the sample is going to lead to cracking further. And also effect of presence of residual or applied stresses can also lead to stress corrosion cracking. And hence all these three problems we see is not a simple problem and it has to be dealt with. So eliminating porosity is one of the important steps for quality control of AM. So if you want to really put your additively manufactured component into service, porosity has to be eliminated by any chance. Now, so as such, we can see pore is a hole or like something like that, but it's not so simple when it comes to AM builds. There are three types of pores that has been identified for AM processes. So first one is called the type 1 pore. So the type 1 pore are perfectly spherical pores that form due to entrapment of shielding gases. So what happens is like the gases gets trapped within the melt pool, and that is not able to escape due to the vapor pressure. And so this is entrapment of shielding gases is seeing in one particular direction, but it could also be due to the powder composition also. So let's say there is oxygen or nitrogen content, heavy oxygen or nitrogen content. Let's say the powder got oxidized, or the powder was, see, we generally used gas atomized powders rather than argon or atomized powders. We are using nitrogen atomized powders. So in that case, the nitrogen the nitrogen gas could form. So all this is going to create these spherical pores. But the good news about this type of pores is that they are typically not detrimental because of two reasons. One, they are spherical. So spherical pores are not a serious issue. And secondly, they are only few nanometers to micrometers of size. They are not very huge pores. So type 1, and typically, even if we do several processes to remove porosity, removing type 1 pores is not so simple because of its small size. But still, since they are not too huge and their shape is, they don't have any they don't act as any local stress raisers, it is not a serious issue with type 1. But type 2 is the most serious pore which you can have in an AM additively manufactured build part. So they are formed due to the AM process related factors. For example, thermal stress induced cracking, incomplete melting of powders, and this third one is the most important one. I think many might have known, it's called the balling. So in balling, what happens is you can see literally a ball kind of feature standing over the melt pool, because it is not able to overcome the surface tension in the melt pool. And the biggest, and why I call this very dangerous is because of its shape. Type 2 pores are very sharp, have very sharp edges, and their size can be between few micrometers to even macrometer size, like few and so on. And these type 3 pores is caused by lack of fusion. So as the name, they even call it a lack of fusion pore too. So what happens is, as we saw, first layer is of powder is applied, and we are rastering the laser over it. And the second layer we are applying, and again while rastering the laser in the second layer, there is incomplete melting. That is, there is no good fusion between the consecutive layers. So this is typically a interlayer cracking. And this interlayer cracks will be generally of lesser circularity. So it won't be as spherical like the type 1 pores, but they are of lesser circularity. So these are some of the types of pores which are being seen which are found in one of our AM builds, I would say. So you see that the type 1 pores here, like they are more or less typically spherical. The type 2 pores here, which are like, no wonder they are dangerous, as you could see, they are pretty sharp, and they are surely going to act as stress raisers. You can see this one, and so on. And type 3, you can clearly see a melt pool will be generally a cup-shaped melt pool like this. And you see that clearly there is a lack of fusion happening here, which is a type 3 pore, which is, as I mentioned, this is the reason why it is called low circularity, and this is more or less circular. Okay. Now the porosity measured for this mill using the Archimedes method is around 3%, which is an alarmingly high porosity. Okay. So what are all the ways to mitigate porosity having a porous AM build? So what if a build becomes failure, we always need not throw it out because we have spent a lot of energy, and yeah, they even charge us for doing additive manufacturing builds here. So there are two ways to mitigate. One is design an appropriate post heat treatment schedule, and second one is optimize the printing parameters. So when I project these two solutions for everyone, it is it's like a kind of common sense to say that yes, before you start printing, just optimize the printing parameters for the AM process, and then for the particular process, and then you build all your tensile bars and so on. But we need to understand the fact that for in many cases, we won't have enough powders. Like we are always not having kilos and kilos of powder which we can lavishly use it. Sometimes the amount of powder available with us might be pretty low. If that is going to be the case, to optimize the printing parameters, what we generally do is we build cubes of different printing parameters, like with different scan speed and laser power, and we print the cubes, find the porosity levels using Archimedes, and do a second level of checking with the closed pores, and then we figure out. But always we don't have the liberty to, we need not have the liberty to use. So, and also if you're working with a typically new material which you either designed by yourself, or it's a material which has like you don't have any parameters available in literature and so on, the best way is to get the print done with one of the factory default parameters which is already available in the machine, or use the one for which has been published for some steel which is similar, and then design an appropriate post heat schedule. So in this talk today, I will be mainly dealing about how to design an appropriate post heat treatment process to reduce the porosity. Okay. So the post heat treatment, what I am going to propose is hot isostatic pressing. So this hot isostatic pressing is a well-known process. Many of you might be knowing. The thing is, like, we will have a pressure vessel, and which we will keep our component, and there will be a heater, and the pressure is going to be applied isostatically, which means in all the directions we are going to give equal pressure, and we are going to use an inert gas atmosphere to avoid any oxidation or other related problems. So why we have to go for this hot isostatic pressing is because, so yeah, as I mentioned, we are going to do it for high pressure and high enough temperature in an inert gas atmosphere, and it is going to close the pore. So what we want now is a pore closure, either collapse of pores or pore closure. So the pore closure or the collapse of the pores is going to happen through either plastic flow or through some material transport. But why HIP? HIP, so as I mentioned earlier, which I emphasize, additive manufacturing is a near net shape forming process. So, but I should not do any post heat treatment process that is going to spoil the shape. Every time we are not going to build only simple cubes or so on. If we are going to build a particular so let's say I'm building a tensile bar, I need to maintain the correct dimensions according to the ASTM E8 standards. I cannot afford to lose the shape or just mess up with the dimensions. So we have to maintain the shape. So in order to maintain the shape, HIP is the best method because you're going to because the pressure will be applied uniformly throughout the sample in all the directions. So we have to do HIP, but we have to design it. So for this reason, we use this. Typically we use this calculation of phase diagrams method. I think we will be having a further talk by Dr. Guru Vidyarthi, who will be explaining this more. I and Guru are former colleagues, by the way. So the fact is that we use, so this is a phase fraction. So these are all the different phases that are forming in this particular steel I'm talking about. as a function of temperature. And I hope everyone will be familiar with the AC3 temperature. AC3 temperature for a steel is the temperature at which the austenite, the material becomes a complete austenite. Now, the AC3 temperature for this steel is going to be 754 degrees C as calculated by this, as calculated using this CalFAD method. However, we want to, due to the errors and because this is an equilibrium thing and there could be some other effects because what we are doing is a completely non-equilibrium process, which is additive manufacturing. To take into account of all that, we are increasing it, the austenitization temperature, like austenitization temperature to close to more than 200 degrees C and setting a temperature of 950 degrees C. And so how are we going to design our HIP process now? We are going to have a heating rate of 15 Kelvin per minute. Like this was done in the company basically. So they have a HIP machine which can only run a heating rate of 15 Kelvin per minute. So we didn't have the liberty to change that. So we just go with it. And a typical pressure of 30 KSI has been found to is found to be good enough for closing pores in AM parts. The time required is designed based on our previous studies where we have already found the optimum homogenization time for this material without pressure. And the liberty what we had was to design this cooling rate. Now, this cooling rate is the worst part of HIP, I would say. Why? Because this cooling rate cannot be as fast as water quenching, what we generally do for heat treatment. So this drop cooling means that like you just switch off the furnace after your HIP process. That is, you heat it, take it to 950 degrees C, hold it for the 60 minutes at 30 KSI, and then simply switch off the furnace. And this is the profile which the company gave to us. So we simulated this profile. And another profile which was given by the company, another cooling profile which was given to us by the company. And we found that this profile was expected to spoil the microstructure lesser. I'll show you in the next slide how it is going to spoil the microstructure, because it is really a spoiled microstructure what we got after that. But the good fact what we should think about is that we should be happy about is that the porosity reduced from 3% to 0.7%, which is a very good number. We have reduced so whatever we want has been succeeded. Yes, we reduced the porosity thanks to HIP, but my microstructure is gone. How? It has terribly coarsened the microstructure. So this is the before HIP microstructure, and this is the after HIP microstructure. So these are the SEM micrographs, and you see that there are two types of faces here. The one with a surface relief and one without surface relief. The one with surface relief is the martensite, which I called as the hard face. You can take it as the hard face. And the one without surface relief is called the bainite, which is the soft face. Now you see that how fine it is here, but after I apply HIP, my bainite is growing, my martensite has become huge and so on. And thanks to this very slow cooling rate over here, that my material has become literally spoiled now. Now, if I'm going to really check the mechanical properties of this material, though the porosity has been closed now, this spoiled microstructure is literally going to reduce the strength of the material pretty badly. So it has. So this is the reason why I'm emphasizing that this is spoiled and so on. How am I going to bring it back? That spoiled microstructure from the spoiled microstructure after HIP is this process called cyclic re-austenization. So this is a post process where like I have to do a grain refinement. As I mentioned here, there is microstructure coarsening or grain coarsening. So what I have to do now is a grain refinement. But again, this is a near net shape processing, and I cannot do any deformation process to bring back. So one of the common methods that is used for doing grain refinement is generally the osforming. If anyone is interested, they can have a read about it. It's called osforming, AUSFORMING. swarming, but that will involve forces, external forces. We don't want any process which will have external forces applied. So we go into this cyclic reaustenization. What are we going to do? We are, after this cooling has happened, we are going to reaustenize, that is, take it to that 950 degrees C again in a furnace without any pressure, that is above the ACT temperature for a very short time. You see, we have done just 1 minute, and then immediately water quench. Water quench, not normal water quench, but ice water quench. And again, one more cycle we are doing. So this is one cycle: heating, holding for 1 minute, cooling, heating, holding for 1 minute, cooling. So this is one cycle. This is cycle 1 and cycle 2. And this is a distortion free and cost effective, because we are not, this is going to be completely distortion free because we are not applying any external force. And secondly, osforming requires a big equipment and so on. What we need is just a furnace and some ice water to get this done. But how did we decide upon these two cycles? There comes the question. We designed initially this, we designed an experiment where initially we will take it to 950 degrees C, but this is all without pressure. Yeah, because, yeah, so we will take it to 950 degrees C, hold it for 40 minutes to make sure that the material has been completely austenitized, and then cool it. So ice water quenching typically has a cooling rate, a ballpark figure will be 130 Kelvin per second. We are trying to use 100 Kelvin per second by but we are trying to cool with the cooling rate of 100 Kelvin per second. Yeah, and then we are doing different number of cycles. So for 1 minute holding at the 950 degrees C. So we have tried 4 different, so 4 cycles. So this is 0th, 1st, 2nd, 3rd, and 4th. And how are we going to do this? This is a new, not so new technique, but something which is known, which is called the quenching dialectometer. So in the quenching dialectometer, it is a very interesting instrument where you have a these 2 push rods where you will place your sample. The sample is going to be sitting between these 2 push rods, and you will have a copper coil which is going to be slid into. And secondly, in the middle of the sample, you will be having a LVDT, sorry, not LVDT, sorry, a thermocouple that is welded that will take care of the temperature. And this LVDT, that is, this LVDT is going to check or record the length changes. So LVDT is known for measuring very sensitive length changes. And you have this gas outlets, as I mentioned, that since we are going to cool it, we will be, in our case, we were using helium. We were using helium gas to cool because here, even argon is not sufficient. We need helium gas to achieve such high cooling rates. So we used helium for literally cooling it at a cooling rate of 100 Kelvin per second. What are we going to get from this quenching dialectometry is this length change, because the length change is going to be measured by the LVDT, but we always take the percentage, that is delta L by L0. That is, the L0 is the initial length, delta L is the change in length, which will be in percentage with and the corresponding and the temperature. So this is going to be recorded. So this will be given by the software directly. So what can we understand from this curve? One thing what we have to understand from this is that whenever there is a phase transformation happening, there is a volume change. The volume change corresponds to obviously a length change. And we can figure out what are all the transformation temperatures. This is one thing. So and there are 2 types of things, changes. One is an obvious change. Like let me explain the curve here. So this is the heating curve where we are starting at around it is a room temperature, let's say 27 degrees C. You keep heating, you reach this temperature here, and there you go. Austenitization. It has become a complete the austenite starts to form, which is the AC one, and the austenitization completely finishes, which is the AC3. And again, it keeps increasing, and then you have some waiting time, either 1 minute or 40 minutes. So that drops down, and then again you are going to start cooling at 100 Kelvin per second, and there you go. It's going to go, and there is a slight slope change. which corresponds to the bayonet start. BS here corresponds to the bayonet start temperature. And then you see this obvious change where this is the start of where this corresponds to the start of the martensite, which is the MS temperature, and this corresponds to the finish of the martensite transformation, which is the MF temperature. And again, it goes back to the room temperature. So how are we going to measure this transformation temperature, which is called the minimum deviation technique? So you draw a tangent and zoom in and check the point from which the line starts to deviate from linearity. And that is how you get the transformation temperatures. And these are all the important transformation temperatures for any steel. And in this case, actually, we are missing, we couldn't record one temperature, which is called the BF temperature. That is the bayonet finish temperature. Unfortunately, for many of the steels, the bayonet finish temperature mostly coincides with the MS temperature. So that's the reason why we were not able to figure out the MS BF, but we could get only the BS temperature, because as you can see, the length change is also not so obvious in this case. So this is a typical introduction for quenching dialectometry, but our purpose is not that. I want to figure out the number of cycles, which is optimum. And so we did two things. One is find the micro hardness, and we find a sudden increase in hardness at 2 cycles. And then what's going on? We do nano hardness. So by doing using nano indentation, and again, what we see is that the bayonet, so in nano indentation, you can find the particular phase and make the indent in that phase. So here I'm showing 2 SPM images here. SPM means scanning probe microscopy, which is generally attached with the nano indenter, such that you can see the topology of you can allow it to scan through, see the topology of the microstructure, and exactly. Now you see, I already showed in the SCM micrograph that the martensite doesn't has surface relief, the bayonet doesn't have surface relief. So you can see that this is an indent, nano indent in the martensite, and this is a nano indent in the bayonet. Now, what is happening here from the nano hardness is that there is a slight change in the bayonet hardness. However, there is a notable change in the hardness of the martensite. And so this is not something which is usual. So then we just probed it further why this is happening, and then we find that the amount of, so we have tried to calculate the amount of bayonet from different techniques like image analysis, dialectometry, and electron backscatter diffraction. Though the numbers are slightly different from each other, but one thing what we can see is that for the optimum number of cycles, which is 2 cycles of reaustenization, the bayonet content is the lowest, which means the martensite content is the highest. As I mentioned earlier, martensite is the hard phase, bayonet is the soft phase. Lesser the soft phase, more hard it is gonna be. And hence the optimum number of cycles was chosen to be 2. And with all this, was I able to reclaim the microstructure or not? Thankfully, yes. So before HIP, that is just the as-built structure. And after the cyclic reaustenization, so after the HIP and cyclic reaustenization, more or less we restored the microstructure. So coming to the bayonet content, which we had measured using, that is the soft phase content, which we had measured using the EBSD. So before HIP, it was 8%. After HIP, it was a big, huge 33%. And now it has come down to 11%. So yes, we are fairly doing good. We have reclaimed the microstructure. But this is not sufficient. So the next step is to do a tempering heat treatment to induce the strength. Why? Because I had already mentioned that copper is going to induce precipitation strengthening, and similarly, addition of molybdenum is to induce the MO2C precipitates. So in order to induce the precipitation strengthening, you have to allow them to temper it. That is, you identify a particular tempering temperature. And again, from this diagram, as I mentioned, since copper and the MO2C are the major, that is curve 6 and 7. Excuse me. So at 550 degrees, close to 550 degrees C, that the content of both 6, that is copper, and 7, that is MO2C, are very high. And so we choose a temperature of 550 degrees C as the tempering temperature. And at this temperature, what we expect is copper and MO2C precipitates will strengthen the HSLA 100 states. And how are we going to figure out the optimum tempering time is by finding the peak hardness. So after doing heat treatment at several different times at 550 degrees C, what we find, yes, for both without cyclic reaustenization, but before cyclic reaustenization and after cyclic reaustenization, we find that 5 hours is the optimum tempering time. So these are all micro hardness measurements which are done with a load of 100 grams and a time of 10 seconds. But one more good news, what we can see is that the hardness of the as-built material and the HIP HSLA with cyclic reaustenization is more or less pretty close, which means, yes, we have improved the not mechanical properties. I would not, that's an overpromise. I would just say, yes, we have improved the hardness. But hardness is not always the indicator of achieving a good mechanical properties, and we need to do the tensile testing. So the stress was a strain curve. So these tests were performed at a strain rate of 0.03 minute per minute inverse. Yes, the as-built steel has a bad ductility, pretty bad ductility. But the tempered HIP HSLA after cyclic reaustenization has a very good ductility. Sorry. Before cyclic. So there has a very good ductility. So let's go look into the actual values. So if you see the actual values, what we see is that the yield strength has improved a bit, just a bit, I would say, but it has improved, but it is well above the design target even before even in the as-built. So the design target is 100 KSI, which I told is pretty close to 700 MPa, and the elongation is 16%. So if you see the yield strength curve, which is this square, the one with square symbols, you see the yield strength in the as-built is slightly lower than the one for tempered HIP after cyclic reaustenization. But the improvement in elongation is considerable. Like you see that here it was a 13% only, the percentage elongation. However, we are almost hitting 20%. Of course, this HIP tempered HIP before cyclic reaustenization has higher elongation because it has more of that soft phase, which is the bainite. However, its yield strength is very low. So from this design, we can clear, and we have achieved the design target. So we have reached close to 20%. So from this design, what we have found is that we now have a steel with very low porosity, that is 0.7% only, but with very good yield strength and very good ductility. Initially, the porosity was high, yield strength is good, but ductility was bad. But now the porosity is low, the yield strength is also high, and the ductility is also high. And this is the success of this design. So from this, the point I would like to make clear is that not always we should be in a position to design the printing parameters, especially if you're going to work on a new material, and we can always get something done with the material, with the parameters what we already have, and just go about with printing. But it should not be a very, very bad print, like it is completely broken into pieces or something. But if we are getting a not considerably, a complete build without any cracks. So the main advantage why we could do this is because first, we didn't have cracks. But only the porosity was the problem, and that we had tackled it using HIP and cyclic reaustenization. So we always it's a failure. It's always like if we have porosity, what I meant is just need not throw into the trash can or dump it. You can still work on it and make the properties to improve. So that's it for today, and thank you for your patient listening. And thank you, and I would like to welcome more questions from.
So whatever is possible, you have to give those things. Okay. Good morning, madam.
Whether it's related to alumni associates
Hello.
or data bank, event register.
I think I'm hearing something. Sorry.
Yes. See, now we are opening the session for question and answers.
It should be
Madam,
Thank
good
you.
morning.
or what are the what is happening different
I'm hearing two voices. Sorry. Like,
Yes.
is it the case?
I have muted one.
Okay. Yeah.
See, the session is thank you, Soumya, for such a good and informative lecture.
No, you're
I
welcome,
like
ma'am.
the
Yeah.
participant. If anyone has any questions, you can ask. Hello, someone is asking a question. Hello.
Yeah, but I'm not able to hear anything, ma'am. I'm sorry.
Soumya Sridhar, ma'am.
Yeah. Tell me, ma'am.
Actually, they have given a question, one chart box. How can we calculate the porosity of materials?
Yeah. So the thing is, first we use the Archimedes principle. We have an Archimedes setup, which can be attached with the weighing balance. So you will calculate the weight in air and then the weight in water, and then so weight in air divided by weight in air minus weight in water into the density of water. So that is the simple equation we use. But the thing is, sorry.
Okay, carry on, please.
Yeah. So that is actually, I would still say a crude method, but a better method rather than cutting every slice and checking the closed porosity. But after you get the open porosity, which is the least, then go for cutting the cross section and checking the microstructure using optical or SEM. And that's in that way you get the closed porosity. In this way, you can ensure that your porosity is the least in all aspects. Yeah.
Other than that, any other methods are there?
Another one is porosimetry, mercury porosimetry and other techniques. But generally, they are pretty tough to find out and tough to do, and they have lot of sample requirements. And secondly, they could be destructive techniques. So what we are showing now is mostly what I'm suggesting now is mostly non-destructive technique. Yeah.
So he is asking the person Ravi. The person is Ravi. That's what he asked.
Okay.
And I wanted to create a porous
Madam, one
media
more question in chat box.
with 3 mm thickness.
For example, I want to create a porous media for 100 mm dia with 3 mm thickness. How to calculate porosity?
And Mr. Ravi, please, your question is not clear.
Yeah. But okay. I am a person who is against porosity. So yeah, I want to mitigate porosity typically. So that is what probably Mr. Ravi is asking about. Might be some mesoporous media or something like that. I think he should check the literature. I'm not sure about it. Sorry about that.
And Mr. Ravi, you can unmute yourself and then you can ask the question. No other questions. And in air parts, how much you can able to unmute yourself, please. Padmalata ma'am, you have to unmute. Give a permission to unmute.
Padmalata ma'am is not.
Madam, good morning, madam.
Yeah, good morning, sir. Yeah.
Madam, just I'm facing problem while I'm going to unmute. Myself Ravi, alumni of IIT Madras, madam. So
nice to meet you, sir.
Thank you, madam. While I'm going to design a porous media in CFD analysis or such kind of things, just I want to create for a backfill of 100 mm diameter and 3 mm thickness. So I gone through some literature. Only 2 literatures I found till date based on the porous media in baffles. So those are taken as 5 mm or 10 mm thickness. So I want to reduce it, but while I am calculating that porous media, I am facing the problem. I gone through the Saha textbook also by heat transfer by Saha, but I unable to get it. That's why enthusiasm is waiting for this.
Typically, I am not a heat transfer person. First of all, I am a
how to
material.
create the porous media. That's enough.
I
To know.
see. I am not so as I mentioned, I am against porosity in this case. But
That's
I would suggest that you check some of the literature which is related in ceramic. Like I have worked during my masters on porous media, like ordered mesoporous materials and so on. Mostly done for ceramic materials, like. You can check some literature. Like my co-supervisor, Professor N.V. Ravikumar, works on it. You can check his literature.
That's why I gone through your Google citations, but I didn't found the papers on this. So
Oh,
anyhow, I
okay.
texted to follow.
No. Like if you want, I can forward it to you. Like whatever porous media I previously worked on, but they are
Okay.
not ordered porosity. Please keep it in mind that they are not ordered pores. But we wanted to check that for weight reduction for space aircraft, not aircraft, for spacecraft. Okay, so we just check the ablation resistance and the thermal shock resistance. I think that is the work of mine you are checking right now is what I'm thinking. Sorry, but 6 years ago I did and I totally changed my field now. But please check the literature from my co-supervisors group, Professor N.V. Ravikumar, and you can surely get a good idea about it.
Okay. Thank you, madam. If not, then I can approach you.
Yeah,
Anyhow, I
sure.
cited
My
in Google
mail ID.
citation. I cited in. Otherwise, just you can share your mail ID, madam.
I think it was given in it's sos57@pitt.edu. If you once get the recording in the first slide, I would have already shown. You can take it.
Okay. Because I have some problem with Adep Kumar also. He is also giving the details, but whenever we are going to text him or we are going to knock him, he won't respond. So I have experience, and directly I contacted him personally when he came for Vivas and such kind of things. At that time also he won't answer.
Okay.
So, I'm sorry to pinpoint.
He is the HOD of MME department in IIT
NIT.
Madras. Please understand that he will be also
No.
busy.
I am asking
but
about
please
Adep
write
Kumar.
to him and
I am saying about Adep Kumar. He's giving like a hero, his contact details, all mail ID, phone number, but he won't respond.
I am not sure about it. But
Okay. Thank you, madam. Thank you anyhow. Right.
Any questions from the topic, sir? Any of the participants?
Hello.
Yeah, please. Yes.
Yeah, good morning, madam. This is Niresh, research scholar from Osman University.
Yeah, please. Yeah, nice to meet you, Niresh.
Okay, thank you, madam. And recently, I done with 3D printing on ALS at LMG aluminum material, and I done with density through Archimedes and what you did say before. So I got the 99% of density. And what is the porosity? Remaining one porosity is the right.
Yeah, that's what. If you get the density, you calculate the relative density, right? Like whatever you get from Archimedes.
So for that, according to that material.
No, Niresh, I think there is a small. Let me make it clear. You get the density from Archimedes, and you find the theoretical density, and then the density from Archimedes divided by theoretical density is called the relative density. And 1 minus the or 100 minus or 1 minus the relative density is your porosity. It's not a directly a 1 minus. No. You have to divide that density, what you get from Archimedes, with your theoretical density, and then subtract it from either 100 or 1 and get your porosity. Then it works.
Okay. Thank you, madam.
No problem.
Hello, ma'am. This is Santosh.
Hey, hi, Santosh.
Hello, ma'am. So my question is, how do you additively manufacture some alloys which are prone for oxidation? For example, if you're going to do some work on titanium-based alloys or something like that. So I am interested in 3D printing shape memory alloys. So most of which are prone to oxidize a lot. So how do we prevent oxidation during this additive manufacturing?
So yeah, is a very important question. First, the purity of the gas that is being sent into the build chamber. Your argon should be as pure as possible. Okay, even a small leak is going to spoil your whole build. Point number one. Secondly, I would suggest this is just based on my thinking, based on what I have seen till now, is that don't have a very slow scanning, so that it can and it may basically what I mean is don't allow the melt pool to remain in liquid for a long time to catch the oxygen from the atmosphere. These are the two things. So your build chamber should have a should be passed with argon, which is of very high purity. And secondly, you have to not allow the liquid to stay as a liquid for a long time. So typically for so let's say you're working on titanium 6 aluminum 4V, let's say, which is the workhorse material, the titanium alloy. I think the parameters are designed in such a way like to avoid all these oxidation issues, I think. And when your build chamber is properly is being purged with the correct inert gas, you should typically not have any oxidation problem.
Thank you.
Have I answered your question?
Yeah,
Also?
yeah.
Okay.
Thank you,
Okay.
ma'am.
Thank you. Any other questions from anyone, please? I'm ready to answer.
Soumya, can you hear me?
Yes, ma'am, I can hear you now.
Possible the other part of your session, the other part. Me now?
Sorry, ma'am.
Can you hear me now?
Yeah, I can hear you now.
Can you focus on the other part to optimize the process parameters in the machine?
Actually, I'm sorry about that, but that's unpublished data. And
Okay.
this is US research naval project. So
Okay.
I can't disclose that. No, sorry about
Okay.
that. I thought when I spoke to you and discussed the topics, I thought I will be able to complete the manuscript, but unfortunately I couldn't.
Okay.
Yeah.
Generally, can you focus what are the parameters we can change? Because you are
yeah.
any
Yeah,
videos
sure.
you want to play and show with the different parameters, how the property, how it is affected with different parameters of the machine.
Okay, so my take on this part is that we know that in LPBF there are several parameters available, like scanning speed. Mainly what we concentrate is the laser power, the scanning speed, and the hat spacing. But there are other things like the outer skin velocity in top skin, and the contour speed. The contour, as I showed you, like once you finish and it goes one round around the tensile bar and so on, and all this. So typically what we do is, my take on this is, don't play with too many parameters. We are going to really mess up. Take only 2 to 3. So in my case, I chose only the laser power and the scanning speed. And I varied based on, so there are there is one particular, a parameter which we can play with, which is called the global energy density. So in the global energy density, it's basically power divided by the diameter of the laser beam into velocity. That is the scanning speed. So we do different cubes. As I told you, we will build cubes maybe 5 cross 5 cross 5 cubes of different parameters. And as I mentioned, we will do find the porosity. And after finding the porosity, we will choose the best one, and then we will build the required tensile bars and cubes, and even for toughness also we can build I guess you might be knowing about the Sharpie bars, which will be used for the impact toughness, the Sharpie V-notch test. We do that and then evaluate the properties. So the main thing is that for this type of steels or for any material what you are going to deal with, you have to figure out what type of properties you are going to study and accordingly make your builds. And for as far as the parameter optimization is concerned, never play with too many parameters. You will be terribly confused as to understand what is affecting what. What is affecting what will become a problem. So as much as possible, play only mainly. This is only my take for LPBF, that is laser powder bed fusion, or otherwise known as SLM. So these two for this process only I'm talking about. But when it comes to other, I've not worked with powder feed. But when it comes to wire feed, again we will have different other parameters like the wire feeding rate, the travel speed, the voltage, the current. All these parameters will play a role. But whatever it is, play with the least number of parameters possible, maximum 2 to 3, so that you can identify the best one. And remaining, you use some default parameters which is already available in literature or already available by default in the machine itself. Because typically most of the machines come with default. So there are certain materials which have been worked for a lot, like Inconel 625 super nickel based superalloy, Inconel 718 nickel based superalloy. In steels, if you see, it is like stainless steel 316 and stainless steel 304. And in titanium alloys, it is titanium 6 aluminum 4V. And in aluminum alloys, you see aluminum 10 SIMG. There is one other alloy. So typically, you'll have some 8 to 10 alloys for which extensive work has been done. And also the company, the manufacturer himself would have optimized the parameters for this, and he would have given us, he would have stored it. But the problem is you can't see those parameters. So just change certain parameters and take the remaining and set the remaining parameters what is given by the factory default setting itself. This will be my take on optimizing the build parameters, optimizing the printing parameters, the strategy.
And what about sleeve analysis, madam?
Sorry?
What about sleeve analysis for powder particle size?
Okay, particle size. Yeah, this is a good question. Thanks for asking. Particle size, there are two. I have two different school of thoughts for this. Okay, one, either you believe the manufacturer who is giving you the powder, okay, and just use it. Okay, if not, you have this laser powder size analyzer, right? You can use that and get cross-check the D10, D50, D90, average size and all these things. But typically when we have these pure pre-alloyed powders, what we buy, we have several vendors here within the US from whom we buy. We generally believe, not say believe, but take the values which are given by the vendor assets. Sorry. But when we are mixing two powders and trying to create a gradient alloy, that is one of my research interests here currently during my postdoc. We do particle size analysis because we are mixing two powders of different sizes. Typically, they should be spherical in shape because we buy only gas atomized powders, but they will be of different sizes, right? So you need to know that, as I mentioned, the average D10.
And also different melting point zone.
What is it? Can you please come again? Sorry?
And when you're using the different particle, different powders, and the melting point also different. So that is the main effect zones.
See, melting point, you need not worry much because you're going to hit a laser to melt everything. Okay. So I think that should not be a concern. Is that what you're asking about? Am I making sense to you? Sorry. Happened.
Nilesh, you want to continue? Any more questions, Nilesh?
No, no,
Is
madam.
it
No,
not?
madam. Thank you, madam. Thank you so much.
Oh, okay. You're welcome.
Madam, one question they have posted. Apart from titanium and aluminum alloys, can you suggest any novel materials in AM?
Mm.
In
Where
additive
scope of
manufacturing,
research.
where scope of research is more?
So naval materials are more or less fixed, I would say. Yeah, titanium, aluminum. So anything which is weight saving and has good corrosion resistance can go for naval, but also with good manufacturability or processability. But typically for the applications which I spoke about, as I mentioned, these are all steels which are being researched for the last 70 to 80 years. I don't think there are new materials anymore. We can propose, but to get it certified, it is going to take another 50 to 60 years for sure. Probably we can just propose, okay, this could work for this could work for this, but whether it is really gonna work for it, you have to literally put it in the sea and check. So yeah, so naval materials where new scope is, I would say, okay, I think till now titanium, aluminium, and steels, some types of steels are only used. But if there's any of these criterion which is a new material that that reaches this criterion, like cost effective with good processability and weight saving, like the weight is a concern, right? For because the ship has to float in the middle of the ocean. So weight saving and all this good weldability and all these things, I think it should, if you can design such a material, yes, you have found something new for naval application. Yeah.
Madam, one more question. How can we implement HIP for complex shapes?
Complex shapes, I think any shape should work for HIP, whether it is complex or simple. So I have done for certain samples which have a 0.2 notch, but after HIP, even after HIP, that 0.2 notch was intact. So I don't think HIP is like, oh, complex, it is going to spoil. No. Since it is a hot isostatic pressing where isostatic pressure is going to be applied all around the sample, my thinking is that however complex it is, it should not be a problem. It should typically do the pressing and give it back to you, kind of. But maximum what I have tried is a tensile bar and a Sharpie bar with 0.2 notch. There was no distortion. Intact the shape was.
Any more questions from the participants? I think no more questions.
Yeah.
Thank you. Thank you.
Yeah.
Thank you very much, Soumya, for your very good and informative presentation.
Yeah. So, ma'am, so thank you very much, Padmalata, ma'am. This is my first talk I am giving after coming to the US. So thank you very much for giving me this opportunity. And Saraswati madam, I saw her face. Yes, I have seen her in 2017. I hope she's here somewhere. But yeah, if she's not here, please let her know that I remember her face and I do remember her. Thank you for giving me this opportunity, ma'am. And I'm happy that I was able to share a part of my research to others in the research community, which will be, and I hope it was helpful and useful for others. Even a minuscule increment in knowledge today is a big success for me. And if you get any feedbacks, ma'am, please do forward it to me.